Hello and welcome to pbspec, the channel about vibrational spectroscopy. Today I'm talking about what is infrared and Raman imaging. This video is part of a series giving you an introduction to imaging by infrared and Raman spectroscopy. In this video I will cover two topics. First, the motivation to perform imaging experiments, and second, types of imaging setups. Let's start first with why imaging at all. Consider the basic setup of the spectroscopic experiment, a source for electromagnetic radiation which is shown onto the specimen, and a detector which records radiation which is subsequently processed to result in a spectrum visible to us. If we look closer on our specimen, we see that all of its individual components contribute to the resulting spectrum. The widely available FTIR, ATR spectrometers are a typical example of this measurement approach. In the picture you see that the specimen, in this case powder, is measured at once. In such an experiment, the result of one measurement run is a single spectrum, regardless of how many chemical components are present in the specimen. If the sample is homogeneous, then there is no problem at all with this approach. However, sometimes we may be interested in a more accurate analysis of the sample, meaning that we want to understand how the individual chemical components are spatially distributed. Since the basic spectroscopic experiment yields only one spectrum, we have to somehow focus the radiation beam and move it across the sample in order to have a chance to unravel the individual constituents. Let's talk now about experimental setups enabling vibrational spectroscopy to be used as an imaging method. Therefore, our basic setup has to be extended. One thing we need to introduce is some form of beam focusing, which I call focus unit. Since we deal with electromagnetic radiation, it is obvious that we can use lenses to focus the beam. Microscopes are therefore useful and can be coupled to spectrometers. Interestingly, also cantilevers can be used to focus. I will explain this later on. Another thing required is a device which moves the focus unit relative to the specimen. I will call this the moving unit. In most systems, it is a sample which is moved relative to a fixed focus unit, although exceptions exist, and sometimes even both units contribute to the movement. For example, the sample stage covers movement in the X and Y direction, whereas the focus unit covers movement in Z direction. In summary, the general concept of imaging in spectroscopy is raster scanning the sample to generate information at spatially different positions, which will then be processed into pixels of an image, hence the name. On the next slides, I will dive into 5 general experimental setups of how FTIR and Raman imaging can be performed. The first imaging setup extends the basic experiment with an objective resembling a microscopic system and a scan stage. In this first setup, the radiation is passed through the specimen, therefore requiring at least some transparency of the sampled material. This setup is typically used in infrared microscopy, operated in transmission mode. Compared to other imaging setups, the spatial resolution is in the micrometer range and not all materials can be probed due to transparency requirements. A similar configuration is used in the second setup. The only difference is that here the reflected, re-emitted or scattered radiation of the specimen is collected by the same objective which also passed the incoming radiation forward. This setup is often used in infrared microscopy in reflection mode as well as in Raman microscopy. Transparency of the sample is not a prerequisite for measurement anymore, however, still determines the sample's volume which can be probed. Such systems are kind of easy to operate because their handling is very similar to that of a normal optical microscope, as is the sample preparation. The third setup is a specialized one typically used for infrared microscopy. Instead of passing the radiation and collecting the signal through air, a crystalline tip, often germanium, is pressed onto the sample. Inside the objective, the radiation is passed over mirrors in the tip and through the crystal back into the collecting pathway. The operational principle is that of FTIR ATR machines. In fact, you can understand it as an ATR unit which is pressed onto the sample instead of the sample being pressed onto the unit. The incoming radiation is totally reflected at the inside of the crystal and does not reach the sample. However, an evanescent field is created on the sample side which interferes with the specimen. This information couples back to the other side and dampens the reflected radiation. Therefore, the name ATR, attenuated total reflection. This procedure is typically used in infrared microscopy. In comparison to transmission and reflection mode, spectra with high signal-to-noise ratios can be obtained, given that the crystal tip is in intimate contact with the specimen. Be aware that this means that this is not a contact-free method. Depending on the probed material, visible indentations can be produced, which can be problematic when working with delicate materials. Depending on the material, its refractive index may also prohibit the use of the method. With the fourth method, we enter super resolution imaging, meaning that the resolution is increased with respect to classical diffraction-limited microscopy. This method exploits the extremely short-range near-field interaction between a pointed probe and a sample. In addition to the objective, a cantilever is placed into the beam and very close to the sample, the tip almost touching it. However, in contrast to the previously explained ATR microscopy and to atomic force microscopy, the tip is still operated in non-contact mode and ideally never touches the sample. The incoming light excites a collective oscillation of electrons, which can be understood as a cloud of electrons moving back and forth. This is called a plasmon. The plasmonic field strength increases with decreasing curvature, therefore the electrical field is highest at the tip of the cantilever. We can think of it that the tip focuses the light, and molecules in the immediate surroundings of it will experience the highest field strength. Because the IR and Raman signal intensity also depends on the field strength, so that higher field strength means higher signal, the molecules in close proximity to the tip experience the highest field strength and therefore produce most of the scattering relative to neighboring molecular regions. Because scattered radiation undergoes the same enhancement process, both incoming and outgoing radiation are intensified. As this signal enhancement depends on the distance from the tip to individual molecules, those molecules closest to the tip will make up for most of the total signal reaching the detector, and that is how super resolution is achieved. The exact interactions, however, are much more complicated, involving also atomistic effects, and are not yet fully understood. The corresponding methods are called nano-FTIR when operated with infrared radiation and Tip-Enhanced Raman Spectroscopy, often abbreviated as TERS. The fifth and last method in this video is utilizing only a cantilever and a scan stage. Instruments normally have objectives, but only for sample placement and cantilever alignment, but they are not necessary for the measurement itself. Here, infrared radiation is shown onto the sample, exciting molecular vibrations. The cantilever setup is like in normal AFM instruments, meaning that the laser is pointed onto the cantilever tip and reflected to a photodiode, therefore measuring any cantilever movement. The difference to conventional AFM is that not the cantilever itself is brought into motion, but instead picks up the vibrations of the surface, which is molecular vibrations induced by the infrared radiation shining on the sample. The cantilever motion is recorded and then deconstructed into its frequency components. From these, a conventional IR spectrum can be constructed. This method is called AFM-IR. So it's time to wrap up the different ways how to perform imaging by FTIR and Raman. I tried to cover the basic principles instead of individual methods. There exist plenty of ways to modify these measurements, which are often given specific names, creating a jungle of abbreviations, sometimes even difficult for experts in the field. However, with this overview, you should have the necessary background to also understand variations of the methods I covered here. We can discriminate setups which are not physically touching the sample, because only light is used to probe the sample. This is classical IR and Raman microscopy. On the other hand, there are methods which require getting into contact with the specimen. Here I covered infrared microscopy utilizing ATR objectives and AFM-IR. I put nano-FTIR and TERS in the middle, because although they are contact-free methods, the tip-to-sample surface distance is in a nanometer range, so close that if the surface is not super flat, in practice you will unintentionally touch the sample sooner or later. All methods have in common that they utilize scan stages, which move the sample around so that a raster scan can be performed, ultimately resulting in an image, which gives name to the presented methods. So long, this was pbspec, the channel about vibrational spectroscopy. Thanks for watching.